In this video, we're going to take a look at the matrix representation for a graph. So we already have some idea what a graph is, right? It's kind of this thing up here. My problem somehow, right, is I need to represent it in memory. I need to represent it before I can have algorithms that do interesting stuff over it. So what will I look at doing? Well, I can look at this graph here and I can say, oh, you know what? It has, say v number of vertices where v equals 5. Why don't I just create a 2D array or a matrix that's v by v, so 5 by 5 here, and basically use each cell as a Boolean that says yes or no, are two things connected or not. Okay, so this is the basic idea of a matrix representation. We have a matrix where every single cell is showing the relationship between two nodes as indicating is there an edge there or is there not an edge there. And for this, I'll use a Boolean array. So that picture up top that I have is actually encoded in the bottom diagram, right? So I have here, right, this picture here, and you can look at it. So you can see here in the diagram, it shows, I look at, 0 over here by 1 over here, right? So I look here and here, and notice it says true because those things are connected. So this over here is actually corresponding to this connection over here, right? This one over here. Now, something that's a little bit odd here is maybe the fact that this thing is symmetric. And so you can actually notice this node that I'm talking about is also over here as well, right? So 1, 0 is there as well as 0, 1, right? So it's kind of like both sides. Somehow what that's representing is that it's like either direction, right? So I can move 0 to 1, or I can go move 1 to 0, right? I can go either way. And the fact that my graph has basically those two different entries there, right, is basically reflecting that. Now, one observation here, right, that's kind of an aside is I don't really need half of my graph, right? So I know actually in an undirected situation, right, where it's like, well, I'm always allowed to go back and forth wherever I'm at, right? From two, if I'm looking at an edge, or I can traverse either way, right? It's all going to be fair game. Basically, I don't need half of that matrix, right? So I could actually think, even if I really want to, about just scratching out this side and just focusing on one side, right? If I want to, I could do that. And sometimes people do that because it's a more efficient thing, right? Half the amount of memory you need. But by default, right, we'll say it's this whole thing. Now we can look, elsewhere, right, and we can kind of double check to see where the logic's working out. So for example, let's see, 4 should be connected to a bunch of stuff. So let me see what 4 looks. Looking over here, 4, oh, that's connected to 1, 2, and 3. Hey, that's what I see in my diagram, right? And if I look at 1, 2, and 3, I'll see, right, so this is 1, 2, and 3 over here. I'll see that those are, connected to, 4 again and again and again, right? So everything's kind of, looks like it's working out pretty well. Let's see, as one more example, let's maybe add one more connection. So let's add a connection between, I don't know, I guess we can only really add one connection here, or one interesting connection here. We can add maybe a connection between 0 and 3. Take a look at the graph. How would I add that? Well, I'm going to look at 0 by 3 over here, right? So add that. 3 by 0, I need to add it kind of both sides, and there we go, right? So these over here, right, those two correspond to me doing that, right? To me basically adding that node or that edge over there, okay? So this is the very basic, matrix representation of a graph. So let's think about it and let's try to figure out, how performant it is. So the first question we're going to ask is, of course, how much space does it take? So what do you think? How much space does this take? Well, here, right, it's going to take v squared, right? So the amount of space is basically going to be tilde v squared, because that's the size of the matrix, right? You have v over here, size of the matrix. So square that, right? It's a matrix. That's your size, right? So this is basically the amount of entries we expect to have, right? So decent amount of space. Hopefully we can do a little bit better. That square is a little bit bad. We already know, right, that some of the graph isn't really used, right? Because it's like, well, this diagonal, I could throw out that side. And then we also know, right, there's a bunch of empty spaces here. So it's like, well, do I really need those or not? Those are empty spaces. So yeah, that's how much space it takes. Next question is, does this support self loops? What do you think? So self loops, there's not any in the picture, but yes, it can support them. So what would it mean if I had, for example, a self loop on 1? Well, how did my picture change? What do you think? Well, it changes by having a value over here, right? So actually that diagonal is just for self loops, right? So it's basically me saying, is something connected to itself, right? That's what the word the diagonal is meaning. And so when I have a self loop, that's where I'll place my thing. So here it's like all of a sudden I added over there, now 1 links to itself. If I put it over here, that means that 4 links to itself, right? So I have that self loop notion there. All right. So we've talked about this, What about parallel edges? Does this thing support parallel edges? No, not as it stands, right? Because you basically just have true or false, are these two things connected or not? That basically says that there's 0 of them or 1 of them, right? I don't have any other values I could possibly have. I could maybe support parallel edges by having, an object there that tracks all that stuff, but out of the box, it's not supported, right? So for this, I would say, that doesn't really support it right now. And so the book doesn't really overall bother with this approach a whole lot. I mean, obviously we're going to discuss it here because people should know what they are, but in general, right, people don't use them a lot because actually you have the space reason, right? So that is a lot of space to commit to, right? Especially if your graph is very large, that v squared can be pretty large. So a lot of times people won't use this representation. So you can maybe ask yourself, right, why would they even use this, right? Why is this worth talking about? Is there anything that this matrix might do really, really fast? And so there was at least one thing, and you can think about this more on your own, but at least one thing that they do really fast is they give you a fast way to check to see whether two nodes are connected. So if I want to know, is node 2 connected to node 4, it's constant time. So imagine this is an array. It's going to be constant time for me to look at and say, oh, you know what? 2 is connected to 4 because I can jump to there, right? I can basically check of, if I have, G, I can do a G of, 2, 4, and then I'm done, right? It's really easy to check to see whether two things are connected. I can do that basically in what looks like constant time. So that's a nice feature, right? If I want to check to see that two things are connected, I can do it in constant time. All right, so that's all I got for matrix representations. In the next video, we'll take a look at using a list to represent a graph instead, which will end up being just a little bit more space efficient.